So hello, everybody. On behalf of the steering committee of the Commission on Global Geochemical Baselines, I would like to welcome you in this webinar on compositional data analysis. This will be presented by Eric Grunsky and Michael Greenacre. I will give you some general information about the meeting. It's a 3 hours webinar we are having, and we will have it in 2 slots. So there is a break in the middle. We will try to have some times for questions before the break and then in the end again. But during the webinar, you can leave your questions or comments for discussion, points for discussion in the chat. Okay, so in the end, I will keep an eye, observe all this, and we will have the opportunity to discuss it. We will try to have a slot like 5 minutes before the break, and then in the end, and even we can stay longer afterwards if you like. Okay, I would ask you to ensure that you have your microphones muted while we have the presentations. Also, as you can see, we have the automatic subtitles in the bottom. I think you are able to enable or disable this. You have the control. And now I would like to ask Alekos Dimitriadis to say a few words about the commission, our commission, that it operates under the auspices of the International Union of Geological Sciences, I remind you, and then make a small introduction for the presenters, and then we will start. Alekos.
Thank you, Ariadne. Now, this is the first webinar of the IUGS Commission on Global Geochemical Baselines. And it's, let's say, it's a test run for future webinars that we will be having during the next year. First of all, I would like to thank you on behalf of the steering committee of the IUGS Commission on Global Geochemical Baselines for your participation. And we also thank very much Eric Grunsky and Michael Greenacre for volunteering to give these lectures. And I'm sure you'll find them very interesting. I'm not going to say much about them because you will find their short CVs on our website. They are well known throughout the world, and you will see why in a few minutes. What else? Anyway, Ariadne will be coordinating the Zoom webinar, so you'll not hear from me again. So thank you very much.
So I think we can start with our program. Eric goes first with a small introduction in compositional data for geologists. So Eric, if you start sharing your screen.
Okay. Is that visible?
Yes, it is perfect.
Okay, good. All right, well, welcome, I guess, good morning, good afternoon, good evening, everyone. Welcome to this session. I hope you'll find the sessions that Michael and I present interesting, but I don't know if you'll find them as exciting as the new James Bond movie that I watched last night. But we've spent a lot of time looking at geochemical data over the years, and hopefully we can provide you some insight into what we have found. Now, all I have to do, there we go. So the goals of geochemical data analysis, we want to detect inter-element relationships of geochemical data that reflect mineralogy or molecular associations and describe or infer geological processes. And we also want to isolate atypical observations or groups of observations that are potentially identified with processes of interest, whether that be mineral deposits or a hazardous environment or alteration or mapping lithologies. That's a very short description of all the things that might interest us in looking at geochemical data. And in particular, looking at geochemical survey data, it provides a sort of a baseline for mineral exploration, geologic mapping, and providing baseline values for environmental studies and land use purposes. And so geochemical survey data are a rich source of information for geological, geochemical, environmental, and climatic processes. And nowadays, more than 50 elements can be analyzed at sufficiently low detection limits. And that geochemical data reflects processes that form or affect mineralogy. And so these data represent a multivariate data space over a 2 or 3 dimensional geographic space and time. And geochemical sample media is very important. The choice of sample media reflects or different types of processes. The method of sample preparation affects the analytical results, where we're looking at sediments, what size fraction you use, and whether the material is pulverized, milled. All those things will affect the results. The method of instrumentation affects the analytical results, whether you're using ICP or mass spectrometry or XRF, they all give you slightly different results. And then the spatial density, or what's known geostatistically as support, affects the ability to detect various processes at geospatial scales. So for effective geochemical data evaluation, we know that there's an ever-increasing number of data sets collected by both industry and government that provide geochemical data at regional and minerals camp scales. And modern methods of data analysis integrate both the detailed and regional data with the expectation to recognize mineralization or vectors to mineralization. And integrating regional and project-specific geochemical data requires careful evaluation to ensure that the data are properly leveled against a common standard. This becomes a problem when you're trying to integrate data that's been collected at different times using different analytical methods. And then the role of standard reference materials in geochemical quality control and assurance cannot be overstated. It's very difficult to merge data if you haven't got some common standards by which you can assess the amount of leveling that might be required. And the sample design should be of sufficient density to provide information at the scale of interest. And what I'm talking about here is the geographic density, whether you're sampling at one site every 1 square kilometer or one site every 400 square kilometers, you're going to pick up different kinds of information at those scales. So we look at the geospatial scales of surveys. We can consider the continental scale at 1 to 500,000 to 1 to 1 million. And typically sampling at that scale, we can map large crustal blocks or tectonic assemblages. And we can look at the regional scale, which is 1 to 50,000 to let's say 1 to less than 1 to 500,000, and we could carry out regional geological mapping. And at the local or camp scale, at a scale of less than 1 to 50,000, we can carry out exploration scale studies and detailed geologic mapping. Excuse me. So at the continental scale, we have 2 examples here, the USGS soil survey, where we have one site every 1,600 square kilometers, or a 40 kilometer by 40 kilometer square. And then the National Geochemical Survey of Australia, which is one site every 5,200 square kilometers. So these are very low density surveys, but we can pick up still remarkable amount of information from those surveys. The regional scale of geochemical surveys, let's say 1 to 250,000, we can look at things like the Tellis water sampling sites in Northwest Ireland, or the Northern Ireland soil sampling sites, in which case the site for the Northern Ireland is one site every 2.4 square kilometers, and in the Republic of Ireland, it's one site every 4 square kilometers. These are pretty dense surveys, and we can pick up a lot of information from those as well. So the key here is looking at the structure in geochemical data. And what we want to do is see structure that defines trends and patterns that are defined by linear or nonlinear methods. And we could look at linear processes in terms of stoichiometry, and that's the ordered arrangements of elements according to atomic forces that form minerals. But there are also nonlinear processes in geochemical data, particularly when we're looking at things like soils or till, where processes such as comminution or material transport and sorting due to gravitational effects can create nonlinear responses or behaviors in the data when we look at it. So we have two kinds of geochemical data spaces. We have the variable space, that's the element concentrations, and we have the geographic space, the geospatial arrangement of the elements. So in the variable space, where we define the stoichiometric structure, we can use statistics and data visualization, in which there are numerous graphical and statistical methods to characterize and describe the variables. And we can use different metrics to display features that are not obvious. And these metrics include things like Cartesian space or log ratios or principal components, independent components, t-distributed stochastic neighbor embedding, plus many others. And each of these kinds of metrics can bring out features and patterns in the data that are not obvious. And within the geographic space, whether we're looking at 2D, 3D, or now even 4D, we're defining geospatial structure and perhaps geospatial structure over time. Geographic representation of data using geographic information systems or image analysis systems, and carrying out geostatistical analysis to study spatial processes. And the geographic metric can be linear in terms of easting, northing, spherical, longitude or latitude, or polar, where it's angular. And these different metrics also, when you look at it in geospatial context, can highlight different kinds of patterns as well. But the key to looking at the geographic distribution of geochemical data is the geospatial coherence of processes. Can you see coherent patterns that are related geospatially that can reflect things like alteration or lithologies and so on? And geospatial coherence is something that's critical in detecting processes. Well, some traditional definitions, not used so much anymore, but certainly are in the literature, what we define as a target population. Those are samples within and surrounding a mineral deposit. And the target population is characteristics of the geochemistry of that deposit. And each mineral deposit type should have its own target population. And then we can define the background population, which are samples, let's say, from a regional survey, or samples not associated with a particular mineral deposit. And the background population may define lithologic variation or other regional geochemical effects and not related to mineralization. So if we look at the behavior of elements in terms of what we can envision mathematically versus what we see when we get material back from the lab, on the left, you see a sort of mathematical representation of covariance of, let's say, gold versus arsenic. But on the right, we see the reality of what we get back from the laboratories. So here we see quantization. We see gaps in the data going along the x-axis. And we see censoring in the sense that there's a cutoff, unlike what we see on the pattern on the left. And the quantization represents precision in the data. So as your values increase, let's say on the x-axis could be arsenic, you don't get so many gaps, or you don't see so much quantization in the data, and that represents sort of improvement in the precision of the analytical instrument. We we distributions in just in a planar sense. On the upper left, let's say principal component 1 versus principal component 2 for some soil geochemistry. We can visualize the density of those points on the bottom left, where we basically created a mesh diagram showing the density of points in those two principal component axes. And on the right is just a color rendering of the same pattern, and we can see where the densities are, which gives us some idea of the how intense a particular process might be. Well, multi-element evaluation, it's advantageous to examine geochemical data using the multivariate approach. Geochemistry is a proxy for mineralogy and is represented by the variability of more than one element. So combining elements reflects the reality of mineral assemblages that comprise Earth surface materials. So from most of this presentation and Michael's presentation, the emphasis will be placed on the multivariate approach to geochemical data analysis and interpretation. So we look at things in terms of a multivariate context. On the left, just a list of various ways we can look at the geochemical data, multi-element geochemical data, things like scatter plot matrix, which is shown on the right. We can look at principal components or weighted sums or cluster analysis or chi-square plots, empirical indices, independent components. I'm not going to discuss these. These are just there for reference. There's a lot of literature on these different metrics. So on the right, we see here kimberlite whole rock geochemistry, looking at selected trace elements, and we can see that there are 5 different kimberlite phases. And you can see that 2 of the phases, the pence and cantuar, form a very distinct trend, which is separate from the 3 phases, early Jolly-Fu, middle Jolly-Fu, and late Jolly-Fu. And so we get some insight just looking at the raw data that there's certain patterns and trends representing processes in this kimberlite data. And another important aspect of looking at data is the transformation. So standard statistical procedures assume a normal distribution, whereas most geochemical data distributions are non-normal and positively skewed, and these represent a mixture of populations. So data should be transformed before statistical methods are used. And outliers should be eliminated prior to the transformation of data. The outliers need to be studied in terms of whether they represent some laboratory artifact or they actually represent a very distinct separate process that is a rare event in the data. The commonly used method for transforming the data is the Box-Cox power transform listed there below, and using the value of lambda, and as lambda approaches a value of 0, it becomes a natural logarithm. And if we then look at a transformation, here is a sulfur, and we see on the left, this is what's known as a quantile plot. The x-axis are theoretical quantiles for the number of points in the distribution, and the y-axis actually represents the sulfur values. And we can see where the data is untransformed. It's very difficult to pick out where the breaks are, where the outliers are. And we can also see there's a lot of censoring in the data, but it's hard to separate the censoring from the lower values of sulfur. If we take a log 10 transform of that sulfur data, we tend to see a much clearer picture of what's going on with the distribution. We can see the censored data being data that's reported at less than the lower limit of detection. And then we see that quantization effect, which represents machine precision as you go up the y-axis. And then you can see certain breaks or changes in the slope of that curve, which represent breaks or possibly changes in process. And then we can see the outliers at the very top that may represent mineralization or some kind of outlier that related to maybe a laboratory effect or some actual mineralization. So that's the first presentation. And if you'll excuse me while I take a sip of my coffee.
Good, Eric. You are in time. We're, well, 5 minutes behind, but I think we are doing fine.
Okay, I'll continue. So the next issue I want to tackle is the closure problem. And this is a critical part of looking at geochemical data. So geochemical analyses are typically reported as a part of a composition, whether that be weight percent, parts per million, parts per billion, grams per ton, milligrams per kilogram. And all values are relative and sum to a constant, whether that be 100% or 1 million parts per million. And even though what you get back from in a laboratory analysis may not sum to 100% or 1 million parts per million, they are still compositional. So therefore, if one value changes, then by definition, all the other values must change to maintain a constant sum. Thus, the variables, whether they be oxides or elements, are not independent, and that violates statistical principles. So statistical methods assume that variables are independent, and since geochemical data are variables that are not independent, standard statistical methods are not valid. So statistical methods are based on values ranging from -infinity to +infinity, whereas compositional data are constrained from 0 to a constant, and that is known, and the data space is known as the simplex. So here's a composition of a basalt, came back from the lab, and on the very left is the lab result, and it totals to 99.37. And we normalize that to 100% in the middle column, and we see the values change a little bit. And then if we actually add a bit of CO2 to the composition, the values change drastically. Now, if we look at the ratio of, let's say, sodium plus potassium over alteration, which could represent some kind of feldspar index, we see that the ratios don't change regardless of how the composition may change due to the effective closure. So the important part here to recognize is that ratios are a critical part of trying to interpret geochemical data, and that using the individual elements themselves may be misleading. I can illustrate that better even with looking at a correlation matrix, where we have on the top 6 major element oxides and generating a correlation coefficients. And then on the bottom, we say this exact same data, but we just use 4 of the elements or 4 of the oxides. We see that the correlation coefficients change. Well, they shouldn't change. But what we see here, the reason for the difference is the effective closure. So it's critical to understand that when you use raw geochemical data, you run the risk of misinterpreting the data. So John Aitchison was a pioneer in developing log ratio approach, but he wasn't the first. I think maybe Michael may have something to say about Paul Levy, who also developed some log ratio approaches to data a little bit earlier than John. But there are 3 critical log ratio transformations. The additive log ratio, known as the ALR, where you take the composition and you take one of the elements as your divisor. So you sacrifice an element to get those ratios. And so you reduce your data space by 1 element. Then there's a centered log ratio, where you take the geometric mean of a composition and divide each element by that geometric mean. It also ends up with a dimension, although you can use all dimensions of the data, it is still a closed data set. The isometric log ratio developed by Juan Hoygasco and Vera Pawlowski back in 2003, where they create balances that result in an orthonormal space. And this is used extensively in some applications, but it is also problematic in some other applications. Well, what about trace elements in compositional data? Because trace elements typically represent much less than the total composition, many assume that the effective closure is negligible, and it can be, but this assumption must be tested before you can accept that. And if the assumption is tested using log ratio analysis, then why not stay in the log ratio space? So that's my approach. There others may feel differently about it, and that's okay. But I think being consistent using log ratios will provide more consistent interpretable results. So the historical use of ratios actually goes quite a way back when rock classifications were petrographically based, and stoichiometry is an essential part of assessing mineralogy. And ratios were introduced to look at the relative values of elements in minerals, thereby reducing the influence of elements not involved in the development of mineral. And this goes back to a monograph published by Cross-Headings, Pearson, and Washington back in 1903. So the problem of closure was recognized a long time ago, and the sort of classical rock classification petrologists back in that time looked at ratios as something very useful. And now in the 1960s, Tom Pierce, who at Queen's University, developed the Pierce element ratio based on the preservation of a constituent within the geochemical system. It is the relative change of a constituent with respect to another constituent that derives compositional variation. So again, you take a element, the one that is preserved or not involved with the process you're studying, let's say like igneous fractionation, and then you divide the other elements by that, and you actually come up with a system where you can define compositional variation related to stoichiometric processes. Now, the reference is listed below, but you should see the work of Cliff Stanley on element ratios. Cliff has worked on this issue extensively. John Aitchison advocated that we should avoid the use of correlation coefficients or correlation matrices because of the closure problem, and he defined what was known as the variation array, which shows the relationships of correlation-like features and covariance-like features of the data. So he defined the variability of the log ratio, tau, where you divide basically it's the variance of the ratios of the elements, the pairwise elements, and then you'd express the mean of the log ratio of the pairwise elements. And you create a matrix known as the variation array. The upper part of this matrix represents the variance of those log ratios, and as the variance values decrease, then you get more similarity between the pairs of elements, and where the variance increases, you get less similarity. And for the mean log ratios on the lower left triangle of the array, you can see that you get mean values represent sort of just how different the elements are with respect to each other. So the consequences of closure, well, closing data results in the possibility of spurious correlations when comparing elements and chemical compositions. And this was already identified by Carl Pearson in 1897. So with the exception of individual mineral analyses, once a composition is expressed as in a constant sum, it is not possible to recover the original molecular contributions without n-member modeling and many assumptions. And I will show this later on. So we also look at the simplex as being a very distorted way of examining data. So if we here look on the lower left, this is a ternary diagram of titanium, iron, and magnesium, and titanium being generally lesser concentrations, the data tends to get crowded along the upper right part of that triangle. But the simplex is highly nonlinear, and particularly in ternary diagrams. Now, if you go to a program called CoDA you can actually center the data in a ternary diagram, and you can then see how distorted the data actually is near the edge of the simplex or the edge of the ternary diagram. It's one of the reasons that personally I don't like to use ternary diagrams, because of this distortion from the simplex, and I think this illustrates this case well. Aitchison defined natural laws, or used the term natural laws to govern the relationships which are based on stoichiometry. And the associations of elements are not random, but governed by atomic forces that result in ordered crystalline structures. So how can we reconcile stoichiometry and a compositional framework? So we look here at an olivine structure. So the blue and cyan represent oxygen atoms, and the green and yellow represent magnesium and iron that occupy the M2 sites in olivine structure. So we see an ordered array that we can then model the behavior of, let's say, the three essential elements of olivine: magnesium, iron, and silica. If you go to Deerhowy and Sussman and you go through the exercise of determining how much in a geochemical composition of olivine represents the M1 site versus the M2 site, and you go through the acrobatics of dividing the molecular weight and the proportions and the number of cations, and you come up with the percentage of composition related to the M1 site and for the M2 site. And as expected from the stoichiometric formula for olivine, it's one M1 site or silica and two M2 sites representing the iron and magnesium. So if we plot those olivine ions in a ternary, or in a sort of a scatter plot here, we can see that silica is random relative to the behavior of iron and magnesium. Iron and magnesium have an inverse association, as we expect, because one substitutes for the other in the olivine structure. But the silica doesn't change, nor should it, because nothing substitutes for it in the olivine structure. So here we see sort of the true behavior of the elements within a mineral. However, when we so we can also then ratio the iron and magnesium against silica, and we get this linear association, which we expect. However, if we represent the data in weight percent, or that is, we close the data, then we automatically introduce this bias, in this case, a negative bias between iron and silica, and a positive between magnesium, where there should be none whatsoever. And again, this represents the effect and the problem of closure. So mineral stoichiometry controls the relative abundance of the elements, and geochemical data are compositional and require the use of logratios to overcome the problem of closure that interferes with the application of statistical methods. And we can use the additive logratio, the centered logratio, or the isometric logratio transforms to help us study the data. So there are two important ways that I define in terms of looking at data. One is process discovery, which is an exploratory approach, or typically known as an unsupervised approach, where we take metrics or coordinates used to discover geochemical processes reflected through element associations and geospatial patterns. And once we have discovered processes, we can then validate those. We can validate those processes or predict them, known as a modeled approach or also supervised approach. Methods for validation and prediction of processes through the use of classification methods. So there are challenges in assessing geochemical data, and this is a bit of a review. So we have the different methods of digestion, limits of detection, instrumentation can affect what we see in the data, and we may be able to level the data where it's appropriate. The censoring effect, samples that are greater than or less than the detection limit, we can remove or impute elements. We have missing values and zeros. We delete elements or compute replacement values depending on the objectives. We have the constant sum or closure problem, the application of ratios and log ratios, and then having adequate sample design, so a properly designed spatial sampling scheme and geostatistical evaluation. Some of these things will be discussed further on. And one question to ask, is there ever a complete composition? Can a complete composition exist? Limitations on machine sensitivity prevent the realization of a complete composition. Is the value of a component reported as zero really a zero, or is it present but just not detected? And therefore, all compositions could be considered as subcompositions. And subcompositions are useful if it can be demonstrated that specific components define a unique process and the other variables only add noise or define processes that are not of interest. So amalgamations, that is combining elements, can offer an advantage by reducing collinearity and some distortion in the calculation of a geometric mean. And this is something that has been studied recently. So I'm going to introduce Kimberlite classification because we're going to show this, Michael's going to show this, and I will also show it again later on. I did this work with Bruce Skarsgård at the Geological Survey of Canada. There is a series of kimberlite eruptions in northern Saskatchewan, and there was a lithogeochemical sampling program at Drill Corps carried out over a series of kimberlite eruptions. The kimberlite mineralogy varies from olivine-bearing magmas to fractionated kimberlite magmas contaminated by crust. We have 283 kimberlite samples and analyzed for a series of 24 elements. This is the top map is the map view, and the bottom figure is a cross section showing the different kimberlite eruptions. And then this is just typical pictures of the various kimberlite phases: the early Jolly-Fu, mid Jolly-Fu, late Jolly-Fu, Pence, and Cantor. And classifying these visually can be quite a challenge. And one of the challenges was, okay, can we look at the geochemistry of these different phases and see how distinct they are? So that's the second phase. Ariadna, how are we doing with time? I'll take that as a yes to continue. Okay, what I'd like to show here are how we look at missing values and imputation. So missing values could be censored values, that is values reported at less than or greater than limits of detection. And they also could be unknown, which are commonly reported as zero or some arbitrary number that you might encounter in a data set. So estimates for replacement are more commonly done by regression methods, and certainly that's what's been done historically in the literature. And it is more difficult to estimate missing values or replacement values for censored data if the data distributions are not normal. So censored data distributions, censored data are very common in geochemistry. You cannot accurately estimate the mean and variance of censored data. It's common practice to take some fraction of the lower limit of detection as a replacement value, whether that be 1/2, 1/3, 3/4, whatever. And that's okay if there's only a few samples in your data set and you've got several thousand. But it can be a problem if you have many censored values that occupy, let's say, more than 10, 20% of your data. So when that is encountered, you have to apply some special procedures. And replacement values are based on the characteristics of data above the censored threshold. And there's a very good paper done quite a while ago now by Sanford in 1993 that highlights just how censored data can affect the calculation of statistical measures. And there were more recent approaches developed by Ron Temple and Phil Moser, a package called Rob Compositions, which makes fewer assumptions about the normality of the distributions and is useful for missing values. And then there's the expectation maximum likelihood algorithm developed by Palarea and Albadejo and Martin Fernandez, a package known as Z Compositions, which provides very good estimates of replacement values for censored data. So we can look at a typical distribution. This is cobalt from a lithogeochemical sampling program. And we see 4 different graphics to describe the behavior of the data. The upper left is a histogram, and we can see the censored data. They're highlighted by the red rectangle. We can see it, we don't see it in the box plot on the right. The censored data does not show up well. We can see it in the density plot or we don't see it very well, sorry, in the density plot. But in the QQ plot, we see the censored data quite well. So one of the things that is important is the graphical method that you use to visualize your data to see just how much of your data may be censored. So imputation is the method of replacing missing data with substituted values we can use greater or less than the limits of detection. And the commonly used methods are nearest neighbor or for Rob compositions, and that's particularly effective for missing values. And then we can use the expectation maximum likelihood method, which is used by Z compositions to estimate values that are less than lower detection. We can also use simple replacement by a constant, or we can use multiple regression. So the software for censored or missing values is Z compositions, Rob compositions, and then there's one called NADA, which is used by the environmental community, so specifically for waters data. And a lot of this was actually founded on work done by the medical community, which has been dealing with censored data, and particularly things like survival rates for a very long time. So epidemiologists have actually been the lead in developing a lot of methodology for this. So if we look at a data distribution, here we're looking at zinc, and we've taken the log 10 of it. And we see here the censored values or data values on the lower part of the quantile plot on the left. We see a continuous range of values till we hit a break, a couple of breaks. And here we might determine a threshold, and anything above that threshold might be considered values of interest from, let's say, a mineral exploration point of view or some environmental point of view. Now, if we impute these censored values, this is what we get for replacement values. Now, these are not real values. They are simulated values that are less than the lower limit of detection, but try and eliminate this truncation or the distortion that might occur when you calculate things like mean or variance. And then we see, let's see here, it's still the behavior where we can see this threshold and we see anomalous behavior. I've also added the percentile ranking on the right here and the actual values on the left. So one way of studying the values of interest in the distribution. So here's, we take this is gallium from a data set, a lake sediment data set, and we treat the data as missing, and we apply Rob compositions. We get data all over the place and things that exceed the lower limit of detection. So it is not a suitable way of estimating replacement values for censored data. Where if we use Z compositions and we're using the expectation maximum likelihood algorithm, we actually get something more reasonable in terms of replacement values that will not distort the estimates of mean and variance in the data set. So Z compositions, there are a number of functions that calculate replacement values. The function LREM implements the model-based ordinary and robust expectation maximization algorithm to impute left-centered values by a coordinates representation of compositional data, which incorporate the information of the relative covariance structure. So here again, on the left, this is barium, and we can see how the values then represent something more reasonable. So when there are many censored values for a given element, the estimate of the mean and variance is less than the true mean and the variance. So when many elements are censored, the combined effect will distort the inter-element relationships and create difficulty in effectively interpreting multi-element signatures associated with background and target populations or processes of interest. So when possible, correct for censoring. And that's where I am finished for the time being.
Everybody see that? Everybody hear me? That's okay?
Yes, it is fine.
Okay. Well, thanks to Eric first for that excellent start of this webinar. And also thanks to Alekos and Ariadne and the support team for this nice event. Because we are running quite a lot ahead of time. So I'm going to relax now instead of rushing through my slides. But I can first make some adverts for my advertisement for 3 books of mine that are available online for free at the site multivariatestatistics.org. You'll get all these slides eventually, so you don't have to write down web addresses now, okay? And also my most recent book, Compositional Data Analysis in Practice, from which a lot of the ideas of my part of the workshop are taken. I think, yes, I have my video on. And the publishers, you'll note at the bottom, the publishers are offering a 30% discount on the price if you order it and give the discount code ASA21. That's people that are attending this webinar. And finally, before I start, I must say I'm a statistician interested in practical yet rigorous solutions to researchers' problems. I'm not a geochemist, but as a South African, my statistical education was always flavored with geostatistics because of the origin of kriging in South Africa. Probably most of you have heard of kriging. In fact, here I am many, many years ago when I was president of the Statistical Association of South Africa, and I'm awarding Dani Greenacre, the mining engineer and statistician who gave him name to this method of kriging. We were awarding him honorary membership of the South African Statistical Association. And that was probably the closest I ever got to geostatistics. Eric mentioned Paul Levy. We know John Aitchison is always attributed to be the founder of the compositional data analysis using logratio approach. And he has, one could say, is the real founder. But there was some antecedents. And this guy, Paul Levy, he worked at Janssen's Pharmaceutica in Belgium. He was head of the molecular biology lab. And he was a very astute statistician as well. Just like Greenacre. Greenacre had a good idea, and he was an astute statistician, and this idea developed into a huge subject of geostatistics. So Paul Levy in the mid-70s, he had a good idea, and he developed a method called spectral mapping, which is exactly what we are going to learn about in my talk now. It's logratio analysis, basically. So he slightly anticipated Aitchison's work. They didn't know each other, and so one could attribute really the subject to both of them. Although Paul Levy didn't publish that much, he was involved in this molecular biology lab. Anyway, my part of my talk is mostly on a little bit technical, but I'm going to make it as soft as I can. And I use a lot of visualization to help you understand the concepts, okay? So you've heard a lot about log ratios. And the simplest log ratios, I believe the most useful are these pairwise log ratios, as well as the centered log ratios. I like to think of them like this. I like to think of them graphically as a graph. Now, a graph has vertices and it has edges or links between the vertices. So yeah, all the parts are shown. This is for the kimberlite data. There were 22 parts. There were 22 parts. So you have, if you think about all the pairwise log ratios, that's 22 times 21 over 2 That's 231 pairwise log ratios, and they're all linked in that left-hand picture. It looks like a doily, and it's quite beautiful, nice and symmetric. It has 231 edges linking all the pairs of parts. In the middle, you have the additive log ratios. These now have a fixed denominator. So I've taken Si, I've taken silicon as the denominator, and all the other parts are numerator parts. So you have 21 ALRs with Si as the denominator. And on the right, you have the centered log ratios. These have the geometric mean of the 22 parts as the center, and they're all 22 parts are ratioed with respect to the geometric mean. Okay, the 22 parts, the 21 additive log ratios with silicon in the middle as the denominators, that's what I mean. Or you could take any of the parts as a reference part for creating additive log ratios. You could take any of them, and you can, let's see, my thing is not changing, not sure why. There we are, okay. You can take any set of additive log ratios, and they explain the total log ratio variance, because all the other 210 log ratios that you can get, all the pairwise log ratios, they all depend on the 21 ALRs, okay? So you can get other sets of log ratios, 21 log ratios in a 22-part composition that also explain the totality of the log ratio variance. And there's one on the left-hand side there. All the links there are log ratios. All the parts are present, and they're all connected to other parts. And there's no cycle. Notice there's no cycle in that graph. There's no closed cycle. And that's what you need to get a 21 log ratios of the 22 elements. It's also called a spanning tree. And that will explain the total log ratio variance in your data. The problem is there's a huge number of such acyclic, well, that means no cycles, acyclic connected graphs. There's j to the power j minus 2. So that would be 22 to the power of 20 such graphs. So you need to choose your particular set of log ratios quite well. On the right, there's a well-selected set of log ratios. There's 8 of them in total. I call that a subgraph. It's not connected, but it's acyclic. There's no cycles. And the 8 log ratios on the right actually explain 95% of the total log ratio variance. So that's a very interesting set of log ratios to use, because you're coming very close to studying all the log ratios. I'm going to explain the selection of log ratios also in this part of the presentation. The nice thing about ratios is that they're easy to interpret, and their summary statistics can be reported, and anyone else doing a geochemical study can compare their summary values of the ratios with yours. As Eric showed, these are subcompositionally coherent. It doesn't matter how many parts anybody else has. If they compare their magnesium to potassium ratio with this kimberlite study, they can compare the ratios because there's no distortion due to the closure. Now, I'm reporting here the medians and what I call the reference ranges of the actual ratios, not the log ratios, because people can think about the ratio perhaps better than they can think about a log of a ratio. And you see the median values of these ratios, and you see the reference range. That's not a confidence interval, but it's a 95% range, which it's estimated, which contains 95% of the individual values. It's a bit like the range you see on your blood test when you go to have a blood test, and you see the range of a healthy population. So those are the 2.5 and 97.5 percentiles of the distribution. Now, you've already seen a triangular plot of a 3-part composition in Eric's part of the talk. And here's another one. It's a 3-part subcomposition of phosphorus, titanium, and potassium of the kimberlite data with its 5 groups of samples. The values of the 3 elements are closed. that's normalized to sum to 1, and they lie exactly in a triangle, and they lie near the titanium corner because its relative values are the highest of these 3 parts in the subcomposition. Now, if I take 2 of the log ratios from this simple subcomposition, and I plot them in a regular scatter plot, you'll see that you see the skewness along the 2 axes. There's a lot of low values and there's some very high values. So you get this high positive skewness in these log ratios. In these ratios, sorry, these are ratios, not log ratios. And then if you do the log ratio, to take the logs of these ratios, things are spread out much more. And that's what we're trying to basically do with the log ratio. We're trying to spread the data out. We're converting a ratio scale to an interval scale where differences between the logs are the logs of the ratios. And that's very, very useful as a starting point, okay? Now, what happens for three log ratios? Okay, for 3 log, but you know, this is a 3-part composition. So how many log ratios does it have? It's got 3 times 2 divided by 2. That's exactly 3 as well, 3 pairwise log ratios. Now I can plot them in a 3-dimensional space. And this is an image of a 3-dimensional space. You've got 3 axes for the 3 log ratios, but you still can't get an idea of what these look like in 3 dimensions. So I've got this animation, which will show you, and clearly you'll see what happens, is that although there are 3 log ratios for this 3-part composition, they actually lie in 2 dimensions. And that's why I've always been saying when you've got a 22-part composition, actually you only need 21. In this way, we have 3 here, so you only need 2. So that's fine. Now we have 1 dimension in the data less than the number of parts when you work with log ratios. So that's quite clear and obvious when you see this in this way. So actually, it's because the 3rd log ratio is always a linear combination of the other 2. In fact, the log of the vertical log ratio you see there, P over K, is just the sum of the other 2. And if you want to think of it as a graph, you'll just have a graph that's, if you have all 3 log ratios, of course, they are forming a cycle. So one of them is redundant, and you only need 2. Okay. So this is what we actually have. We have a 2-dimensional display in 3 dimensions. And so what we can do is we can start finding the axis of maximum dispersion or maximum variance, okay? And then we can find the second one, and that's basically it. We've got accounting for all the variance in that display. Those are actually principal axes. And well, what we do is we lay them flat, okay? We just reorientate the whole story and put the first axis horizontally and the second axis vertically. And that's what the PCA of the 3 log ratios ends up to be. Now, for the 22-part data set, the Kimberlite data set, there are actually 231 log ratios. But luckily, and I'm going to say this many times, the dimensionality is 1 less than 22. It's only 21 dimensional, 1 less than the number of parts. Now, the PCA of all the log ratios, of all those 231 log ratios, which actually exist in 21 dimensions, that's what I call log ratio analysis, or LRA. What you're seeing on the screen now is the PCA of 3 selected log ratios. In fact, there are all the log ratios you can get in this 3-part composition. So this is a PCA of all the log ratios, so it's the log ratio analysis. Now, to do the analysis of all log ratios, when you've got many parts now, there's a very neat result. We only need to analyze the 22 centered log ratios, or CLRs. We don't have to analyze all 231 log ratios. There are 22, in this case, 22 centered log ratios, but they also are only 21 dimensional. One of them is redundant. So here on the screen here, staying with the simple 3-part subcomposition, here is the PCA bioplot of the 3 log ratios at the top And now it's the same as what we had before, but you've got three vectors showing the three log ratios. This is the biplot version. And then at the bottom, you have a CLR analysis where you don't have the log ratios, but you just see the three parts. Okay, you see the three CLRs. And in the CLR plot where you see the three parts indicated, you have to be careful. You should not be interpreting the part labels as the parts themselves. It's very tempting to do so. It's really the links between the parts that indicate the direction of the log ratios. That's very similar to the edges of the graph between the parts that I showed you earlier. So if you look at the direction from TI to P, for example, this vertical arrow that goes downwards, the arrow points to the numerator. So that's really the log ratio of P divided by TI. And if you look in the top plot, you'll see P over TI is vertically downward. So that's exactly correlating with what I'm saying here. And then if you look at, say, K to TI, which is the ratio of TI over K, the log ratio, you'll see that's exactly the same direction as the TI over K log ratio when we analyze the log ratios themselves. So what we do in log ratio analysis is we're analyzing the centered log ratios, and we get all the parts in our display, but we think of it as all the log ratios, which are all the links between the pairs of parts. Now, I just want to rub this in a little bit, what log ratio is and what it isn't actually, because here I've got, starting on the left, I've got X. That's your compositional data matrix. That's closed at the rows, the samples add up to 1 or 100%. Now, I say log ratio analysis is not the PCA of X, okay? Lots of people are doing the PCA of X, and that's okay if they explain themselves, but it's not actually the right thing to do. You often get similar results, but you know, there's one way that you can defend and another way which you can just do and publish, but it's not really defensible. I do mention here that correspondence analysis can be done on the original data matrix X. It's a second best choice, and I'm going to explain that later on why. Now, log ratio analysis is not the PCA of log X, the log of all the elements in X. I say it's not that, but it may be interesting for very high dimensional data. When you've got hundreds or thousands of parts, as you have in some genetic data, you can actually do that, and it's very close to just doing straightforward log ratio analysis. So what is log ratio analysis? Well, log ratio analysis is, the way I've explained it up to now is you compute the CLRs, and the CLRs are row centering the log of X. And so you get a matrix which I call Y star here, okay? And then you do the PCA on the CLRs. And you know, PCA is always column centering the data, so it centers the variables. So if you've just done the row centering, and then you're gonna column center it, that's the same as doing the double centering of the log X at the start, getting a Y and then doing a PCA of the double centered matrix. That's what log ratio is technically. Now, sorry, but here's actually two formula. I promise not to show you much algebra, but just let's say this is the only bit of algebra you'll see. And I wanted to show you the log ratio distance, because when you're looking at a log ratio analysis, you're actually looking at sample points, and you're looking at the distances between them. And you can look at the distances between them, but they are approximations of what distance? Well, it's the approximation of log ratio distance. And that's what the definition of log ratio distance is, in terms of all the pairwise log ratios. You can see there's a pairwise log ratio, there's another pairwise log ratio. We're adding all the square differences between them, okay? Adding them up of all the pairwise log ratios, we're dividing it by J squared, by the number of parts squared. And that's the square of the log ratio distance. So it's really an Euclidean distance. You take the square root now, it's Euclidean distance between all the pairwise log ratios. And we know pairwise log ratios are coherent. And so that's what the distances that you're looking at. But we know the equivalence between the pairwise and the CLRs. So if you do the CLR transformation, which means you take each value divided by the geometric mean, that's the row geometric mean, and you then look at the Euclidean distance between those CLRs, I average them here, I divide by J, that's exactly the same thing. Okay, so you can prove these are exactly the same. And if you want to get distances between log ratio distances between your parts, you can do exactly the same thing. You just interchange a row with a column, the I and the J, and you'll get the log ratio distances between your columns of your data matrix, between your parts. Okay, so here is the biplot version. Now let's go back to the Kimberlite data. We've had enough now of the small data sets. We go to our 22-part Kimberlite data, and we do the log ratio analysis, and we get the log ratio biplot. Remember, I say it again, there is no direct proximity between the parts here. There's a proximity between the samples, the sample points, but the parts are generating log ratios with all the other parts. So if you see these three parts on the right forming a little bit of a cluster, why are they close together? It's because they are forming, if you take any part anywhere else and you connect them to those 3 points, you'll see the directions are very similar. So they have similar log ratios with all the other parts. That's why they are in the same position here. One can show, when you've got a plot like this, you can show ellipses, and these are what are called minimum covering ellipses. And you know, in my second part after the break, I'll show you all the functions and everything that you can use. I won't show you a lot of code, I'll just indicate to you the functions that you can use to get this type of graphics. So these minimum covering ellipses are the smallest area ellipses that actually go that include all the points in each of these groups. These are the 5 phases of the Kimberlite data, the 5 groups. And later on, also in my second part, I will show you how you can show what I call confidence ellipses, which allow you to do some statistical inference to judge whether these groups are significantly different or not. These covering ellipses don't tell you that. They just are geometrically showing where the points are in the 5 different groups. Okay, now what about variable selection? Well, when you do variable selection, we're going to be doing variable selection mostly to explain variance. So the total variance and its explanation is important to understand. In the study of a compositional data set, the amount of information contained in the data is measured by the total log ratio variance. So although there are this many log ratios, j times j minus 1 over 2 log ratios, there's only j minus 1 independent ones, like what I showed you, the acyclic connected graph ones. Only those amount are needed to explain all the variance. All the others would be linearly related to this reduced set. So an optimal set of log ratios can be selected to partially or completely explain the log ratio variance. And we can do this, you know, remember I said there's a lot of possible sets of log ratios that explain the total variance. So we have to devise some, let's say, easy way of choosing. And the easiest way to choose it is a stepwise process. This is not stepwise regression. This is a stepwise selection to try and account for and explain the maximum amount of log ratio variance in the data set. And you can do it automatically using just statistical criteria, or you could do a selection that's guided by expert knowledge. Since at any step, many log ratios will be competing to be selected with almost the same level of explained variance. Otherwise, the process can be automatic, where the statistically optimal log ratio is selected at each step. Or log ratios can be chosen that explain either, well, how I've explained it now would explain the total log ratio variance, which is, you could say, an unsupervised approach in statistical learning, unsupervised learning. Or you could have some objective, like you want to choose log ratios that distinguish or discriminate between groups. For instance, the 5 groups in the kimberlite data. So that would be a supervised way of choosing the log ratio, a small set of log ratios. Right, here's some numerical results on the left first. Some results of the log ratio analysis, and this is a typical output from any principal component analysis. Remember, log ratio analysis is the PCA of all the pairwise log ratios or all the centered log ratios equivalently. So you get the so-called eigenvalues, the parts of variance on the 21 dimensions here in a descending order. You've got the percentages of the total, and you've got the cumulative percentages, and you've got this, what's called a scree plot on the right. And you can see in the 2-dimensional plot that we've been looking at, we have 72% variance explained of the total log ratio variance. And then if you look at the scree plot, there's actually quite an interestingly looking 3rd dimension there. It's extra 12%. There's an extra 12% there. And, it's standing out from the others. From here onwards is probably noise or random variation from the 4th onwards. So if we were doing a more refined analysis, we'd look at the 3rd dimension as well to see what it's telling us. Now, on the right-hand side, we have the log ratio selection, the stepwise log ratio selection. So we can see at the first step, mg over k was selected. It explained 47% of the log ratio variance, and it has this correlation. It's called the Procrustes correlation of 0.688. Now, I've put a special little extra note there what the Procrustes correlation is. This measures the similarity between the geometry of all the 231 pairwise log ratios, okay? Because that's the exact geometry. If you take all of the pairwise log ratios, you have this sort of, let's say, the ideal. It's like the gold standard, if you like. But you don't want to use all 231, you want to choose less. So you're going to compare your choice of a smaller set with this ideal of the 231. And there's a Procrustes statistic called the Procrustes correlation, which measures just a correlation coefficient between the geometry of the reduced set of log ratios and the complete set. So we're already at 0.688. And now you can see the stepwise process, how it's evolved up to 8 log ratios. We've got these first 8, I've sort of bracketed them off because why? Well, I just got to 95.5% variance explained. I thought that was enough. I'm up to a 0.879 Procrustes. So I'm going to stop there in this automatic choice, okay? And then I show you what I get. I've got now 8 log ratios, and then I do the PCA of the 8 log ratios. And I can do the covering ellipses of the 5 groups. And we're going to get, I show you later on when I show the confidence ellipses, we did rediscovering the same configuration or almost the same configuration of these 5 groups in all these different methods, even with just 8 log ratios. Right, now, what about this? I mentioned that we could do a guided selection where we have an expert who knows a lot about geochemistry and who knows about the kimberlite data to actually guide the process of selection. So who's our expert? You can guess who it is. It's going to be E.G. Eric Grunsky. Okay, so I'm also doing something slightly different here. I'm not doing the same stepwise as I did before. I'm going to focus the stepwise process specifically in a supervised manner now on separating the 5 kimberlite groups, the 5 phases, okay? So it's not explaining the between sample variance, it's explaining the between group variance. So the first one that came in here in the first step was CA over RB. Now, this is not a sequence of steps. This is just the candidates for the first step. that are available. And the best one is CA over RB with an R squared of 58.2%. It's got a procrustes of 0.763. The second best is P over RB. It'll have slightly less. This is ordered in descending order of variance explained. As the variance explained goes down, generally the procrustes will also go down. Now, you present this list to the geochemist, okay? And the geochemist looks at it, he can say, oh, I'll take the top one because it's got a nice interpretation, but maybe I prefer one that's a little bit lower down in the list because it's got a much better interpretation and I'm hardly sacrificing anything. So Eric actually chose the third one, okay? You said slightly less R squared, slightly less procrustes, but, you know, minimally less. And so he preferred that one. So then we put that into the model, as it were. We keep that one, and then we say, okay, what's the second one that we would choose, having chosen K over P? Having chosen that one we keep it in, and we see how much we can add by another choice. And so you get a second list for step 2. And the geochemist peruses this, thinks about it a bit, and he says, well, I like that one, okay? I like P over Ni. That's the one I like, and that it's, in terms of R squared, it's identical to the first one, and it's actually slightly higher in procrustes. So that's good. And then you carry on like this. You go to a third step, you get a third list of all these possible candidates for the third one, and the geochemist can choose. In this case, Eric chose this one. And because we have 5 groups, this between group variance actually only lies in 4 dimensions. So if we went to another one, we'd be explaining 100%. But I'm going to stick it just to these 3 because I'm already at an R squared of 99.2% between group variance explained. And I've got a procrustes of 0.961, which means I'm very, very close to the exact geometry of the between group geometry. So here's Eric's only three log ratios that he selected. So you get you could show this in different ways. I've just done the PCA, and it's a 3-dimensional data set, okay, because I've got 3 log ratios. So I'm showing you the 2-dimensional projection of the 3 dimensions. You can see that, remember that I had 99.2% of the variance explained by all 3. And now this particular picture, this PCA, explains 97.9% of that 99.2%. So, you know, we're very close to the between group geometry in this picture, using just 3 log ratios. I've added a little label to them because there's a classification of the parts, which I'm going to turn to now: kimberlite, mafic, and felsic. And the 3 log ratios that Eric chose are kimberlite over mafic part, that's the P over Ni. And then we have the felsic over kimberlite part, which is K over P, and then the mafic over kimberlite part, okay? So he chose 3 that fill into these subgroups, which gives me the idea that why don't I look at those 3 subgroups, okay? Let's just look at mafic parts, felsic parts, and kimberlite parts. Oh, but before I do that, sorry, I was anticipating it, but before I do that, I'm going to do that later on, okay? But I'm first going to look at the additive log ratios. Okay, now I'm pretty partial to additive log ratios, as you'll discover. Additive log ratios for me are one of the best ways of choosing pairwise log ratios. The reason is you only have to consider the reference parts. You don't have to consider all 231 log ratios, yeah? You just have a reference part. The main challenge is how can we choose the reference part? This was the question that was asked previously. Well, I can't use variance explain because all the ALRs with any reference are going to explain 100% of the variance. So I need another criterion. Well, there's 2 criteria I can think of. The one is the procrustes, because that's going to differ. Okay, and also I'm going to be interested in the variance of the log of the reference part. Okay, why? Because if you look at the formula for the ALR, you'll see it's log of a part divided by the reference. It's the log of the numerator part minus the log of the reference part, the denominator part. So if this log of the reference part is very low, is practically constant, then actually my ALR is just the same as the log of the numerator part, which could make a very big simplification of the analysis and the interpretation. Then when you see an ALR, you don't have to think of it as a ratio, you just think of it as almost entirely as just the numerator part. Well, if you look at this list, this is a list that I made considering every possible reference part. And it's ordered in descending order of Procrustes. So at the top, we've got the highest Procrustes correlations we get from ZR and Y. Okay, but they're not the lowest variance of the log of the reference. And you'll see for silicon, it's got a very low variance compared to the others. It's very, very low. The second lowest is iron. But let's take silicon or silica in this particular case, and let's look at all the ALRs with respect to silica. There they are. This is the principal component analysis of the 21 ALRs, all with respect to silica. And we can see a nice big band of parts going upwards and another band going to the bottom right. Again, we get the separation of the groups that we're going to get. Doesn't matter what we throw at this data set, we're going to get the separation of those groups. Now, I just said that if you have a constant like silica in the denominator, that's your reference part for the ALR, you're going to have, you can think of the ALRs just as the log of the numerator part. Well, I just wanted to check that to see if I'm correct. I'm mostly correct. On all these are the 21 ALRs. And on the horizontal axis, you see the ALR, the log of the ALR, okay? Well, actually just the ALR, then, so it shouldn't be the log of the ALR, just the ALR. And then on the numerator, on the y-axis, we have the log of the numerator part. And you can see most of them are pretty much straight lines. And that's because the log of the reference, the log of silica is actually quite constant. But for at least iron and magnesium, and perhaps also over here, you'll see a couple of fuzzy ones, which are not quite following those nice straight lines. But in general, one could make the approximation for most of these parts that the log of the numerator and the ALR is very, very similar.
Michael, we are 5 minutes before the break.
Okay, I'm getting there. Let's see. Yes, okay. I will be finishing in time. Eh? Okay, so on the left we have the CLRs that I showed you before, the log ratio, and on the right you have the ALR using silica as the denominator part. And if you see all these bunches, then you see there is a possibility for reducing, so getting rid of some of these, because they all seem to be correlated, and coming to a smaller set of ALRs. So what I propose to do is to backwards eliminate them, to take them out one at a time from the full set to get a smaller set of ALRs. And here you can see what happened as I took the ALRs out, backwards elimination, I was reducing the variance explained by very little, and the Procrustes also by very little. So in the end, I get just 10 ratios, which give me practically the same result. And if I've got 10 ratios, then I've got also silicon is the denominator part. So I have 11 part subcomposition. I've gone from 22 down to 11. And these 10 that I selected happen to be nicely coinciding with the parts that have the almost a straight line relationship. Okay, I'll go through these last ones fairly quickly. There's the kimberlite, felsic, and mafic components. This is the original logratio plot, but I'm just shading in the three groups of the parts. You can see the definition at the bottom. And I can take just those three parts and do a compositional data analysis of just the three parts. And again, I'm getting something very similar again, similar separation of the groups. I've got one or two slides left now. The one is just to show you cluster analysis of the parts, not of the samples, but of the parts. And you can do it in two different ways. You can cluster by simple amalgamations. That's very easy to understand. When you see two parts coming together, you're just adding their values together. Or you can do what a lot of people are doing now. They cluster by geometric means. And that's in terms of the log ratio distance between the parts. And I'm just showing where the mafic, felsic, and kimberlite parts end up in these two different clusters. And then finally, this is my last slide. For those of you who know about classification trees, maybe not everybody knows, but for those of you who know, we can take the full set of log ratios, the 231 log ratios, and we can do a prediction, a classification of the five phases, the five kimberlite phases. And you'll see the best log ratio chosen at the top, and then you go down the tree. If you know about this method, you'll understand it. And basically, you can predict, based on these conditions in this decision tree, you can predict the five groups. And it turns out that I'm getting almost 95% correct classification based on just a few pairwise log ratios. So, we don't need all the log ratios. We need just a few of them, especially in this data set, to understand the structure and to make predictions and to explain variance. So that's it. I think I must be almost on time.
So we're starting again with the graphical tools. Michael, the floor is yours.
Okay, thank you. Welcome, everybody. Welcome back. And on this title slide, you can see that address that somebody asked me for, the multivariatestatistics.org. You can also see my GitHub site for data sets and R code for various publications of mine. And the most important is the last one, my statistical songs on YouTube. You have to go there and listen to them. Some of them are great hits. Okay, right. Now this, I'm going to basically go through the same slides again. This is going to be much shorter because I'm just going to point out the software that was used to generate these results. Okay, so starting with the graphs, you see I used the iGraph package for drawing the graphs. I'm not giving you CoDA, I'm just mentioning the packages. And then my own package is called EasyCoda. We've heard about other packages, Rob compositions, Z compositions. There's a one called compositions as well. There's the CoDA pack, which is on Excel, I think. And I developed my own package to go with my book, CoDA Compositional Data Analysis in Practice. And the function LR in EasyCoda computes all the log ratios. The ALR function computes the ALRs, and the CLR function computes the CLRs. Okay, so the slide I also had in my first part was to show the medians and the reference ranges. The reference range of a variable is very easy to compute. It's just using the quantile function to get the 2.5% and 97.5% percentiles. Okay. I quite like this for describing individual level data. But now here's something, this is something new I didn't show before. This is now for showing visualizing univariate data. These ideas come from my article that's mentioned at the bottom there. It's an article in Polar Biology. I always say there's nothing better than seeing the data. Don't report means plus or minus standard deviations. That's one of the worst things you can do, although many people still do it, but rather show the values or something a little bit more interpretable. If you have very many values, then probably you'll use box plots. But if you don't have so many values, show the data, show the dots. That's what I'm showing on the left. This is a plot of the log ratio K over RB for the 5 different groups in the Kimberlite data. I have a function called dots, dot in Easy CoDA, or you can download another function, a similar one, plot dot from my book website, or just plot them yourself. It's not so difficult to plot the dots. And then if you're interested in statistically comparing the groups, what you need is a confidence interval for each group mean, not mean plus or minus standard deviation, not mean plus or minus standard error. We need a mean plus or minus the margin of error, or the extent of a 95% confidence interval. So on the right, you'll see something that's my own invention. I call it a confidence plot. It looks like a box plot, but it's not for the individual values, it's for the mean. Each of these confidence plots extends to the limits of the confidence interval, which could be 95%, for example, or higher. The mean is shown as a circle in the middle, and then there's a box that shows a 50% confidence interval. That's quite unusual, but it's just like the box plot does for individual values. So when you're looking at that, you've got a 50-50 chance that the box covers the true mean, and you've got a 95% chance that the wider interval covers the true mean. So I have a function called CIplot_uni for that. And that's also on the website, on the multivariatestatistics.org. You can go to the resources and scripts and you can find that function. Now, here are the bivariate versions of this, of what I've just shown you. You plot 2 log ratios in a scatter plot, or you plot the results from an LRA or a PCA, a 2-dimensional solution. And you can put these minimum covering ellipses over the points. Okay, that function is called ellipsoid hull, sorry, and it's in the cluster package. And in this ellipsoid hull function, you can actually specify a percentage of the points you want to cover as well. You don't have to cover 100% of them. You can cover, say, 90% or whatever. On the right is my version of the confidence interval, but now it's a 2-dimensional confidence interval. It's a confidence plot. It's a confidence ellipse. And that's also used using a function that's part of my Easy CoDA package, or you can get it online from the multivariatestatistics.org. Now, the nice thing about these confidence ellipses is that when they don't overlap, okay, when they don't overlap, especially if you have a high confidence level like 99%, you can be almost sure that the groups are significantly different. But it's always better to do a formal test to get a p-value, just to confirm what you observe. Okay, then what about ternary plots? Well, this is, there's quite a few packages that have ternary plots as an option, and I'm using the ternary plot function in the VCD package. For doing log ratio analysis, I'm again going to use my own software there, the Easy CoDA R package, and I use the LRA function. And then when I do the plots, I do the plot.lra of the result. Okay. Now, to tell you the truth, this plot function does not yet have the options for coloring the different groups and giving different symbols. This will come eventually. I mean, writing an R package you move in small increments. This will come in a future release. So the way I did this plot was I did the LRA, and then from the LRA I can easily export the coordinates from the LRA object. These are given in the LRA object, and then I did the plot by hand, giving the colors and the symbols. Not by hand, but in R by hand. You know what I mean. Okay, I've already mentioned the ellipsoid hull to do the covering ellipse. That's from the cluster package. And now something different that you haven't seen before. Sorry, whoops. No, it's not there. Okay, I thought you were going to see the confidence confidence ellipses, but they seem to have vanished there. Don't worry about that. You'll see plenty of them still coming up. Okay, I'm moving then straight on to the stepwise selection of the ratios. But first, on the left, you'll see that same output from my LRA function, the summary output. And I did that by, first of all, doing the LRA. You can see the statement at the bottom. I do LRA of Kim, that's the data set, the compositional data. And I say weight equals false. Now, you'll see this weight equals false a lot here because I'm not including weights on the parts. This is something I'm not going to go into, not going to treat in this course, in this workshop, but it is possible to weight the parts, and it's a very interesting aspect. In fact, Paul Levy, I mentioned him earlier, his original definition of log ratio analysis included weights. So you can always make the weights equal. And most people are using unweighted or equally weighted parts. And so that's why I always have to put weight equals false to suppress my weighting option. So my result is kim.lra, and then all I do is do a summary of kim.lra. I'll get this list of output on the left-hand side. And then what about the right-hand side? I said, this is the stepwise log ratio selection. I've got a function in easy CoDA, and this is only in this package you'll find this function. It's called step. And so I say step of Kim, and I say weight equals false again, and I save that in kim.step. And then you'll see then in this kim.step, I've got a lot of stuff, including the ratio names, the R2 max, the maximum variance at each stage, the accumulated maximum variance, and then this Procrustes correlations. You can get these 3 columns that you see here, the ratio names, the R squared, the Procrustes. You can get it from these components of the object. Okay, now what about the PCA? Well, PCA, there's a lot of PCA packages, functions in R, in various packages. I just wrote my own. It's a very simple thing to write a PCA function. And so I included that in my easy CoDA package called PCA in capital letters, uppercase letters. And I've got the plot.pca. And so I can do a PCA of some selected log ratios, in this case, the 8 log ratios. And again, I exported the coordinates to be able to plot them in color. Okay, this is going to come. There will be an option in a future version where you can specify groups, specify symbols, and you can specify colors for the groups. There's the ellipsoid hulls again, the covering ellipses. And now we're going to look at the step-by-step, the supervised one. The supervised one, not 2 differences here. Supervised, I'm going to look for group separation specifically. So I'm explaining between group variance. And then I'm also asking my friend Eric to make his choice. Okay. So now in my software, you can use the same function step, but you can see at the bottom, you can see I say n steps is equal to 1. So it means I'm only going to do 1 step. I don't want to do more than 1. I want to do 1 step and stop. And then I ask for the top 15, top equals 15. Usually by default, top is equal to 1. But I'm now going to do 1 step and ask for the 15 competing log ratios to enter. And that's what I got. You can see in the table. And these ratio names, R2 and Procrustes correlation, I get from the components ratios.top, R2.top, and pro.top in this result of the step function. So you remember Eric chose that one. So then for the second step, I had to force K over P into the selection. So, oh yeah, by the way, I just say this is the matrix of aggregated centroids. It's the centroids of my 5 groups. That's what I must use now if I want to do discrimination. I'm not doing it on the original samples, I'm doing it on the groups. Okay, so now you'll see what I do in the second step. I have to force in K over P. So I have to specifically use this option called previous. And previous is equal to the K over P ratio. Again, I ask for 1 step from that point onwards. and I asked for 15 competing ratios. When I prepared this slide, I couldn't, for the life of me, I couldn't realize why I have specified unweighted, equal weights. I say weight equals this list of equal weights. It should work just with weight equal to false, but something I have to check up. There may be some reason why I did that. Anyway, I'll get the second list, okay, and then ask Eric what he wants, and he chose that one. And then for the third step, I have to put the first two in. Okay, I have to put in the K over P and the P over NI. So I put previous equal to that two-column matrix now. Again, one step, 15 competing ratios, and so on. Then I get he selected from that list, he selected FE over ZR, and then I would just take those three and do the analysis. I'm not showing the result that I showed you in the first part. Okay, here, what I'm showing you here is the three amalgamations now. This is now the three amalgamations superimposed on the log ratio analysis. So when I did the log ratio analysis, I realized there are these three grouping of parts. They turned out to be very similar to the groupings, or some of the parts in these bunches that you see going out from the center coincide with kimberlite, felsic, and mafic. So I could actually physically define them, and then I could actually add them to the display. This is what we call supplementary points in this component analysis jargon. That means they haven't been used in the analysis, but they've been added afterwards. Okay, and then what I could also do is I could just, I just did informally, this is just in PowerPoint, I showed where the kimberlite and the felsic and the mafic parts were. And then I could just do an analysis, a separate analysis now, where I've taken the mafic, felsic, and kimberlite. You'll see the statements at the bottom, the code at the bottom. I've made a three-column composition with those three amalgamations. I just normalize in the second line, divided by the row sums, and then I do a LRA of that three-part composition, and I plot it, and that's what you've got here. I could also do a ternary plot of the three parts here. I only have three parts. Okay, now I put the ellipsoids on them, the ellipses, sorry, the covering ellipses. And here we are. Here's an example of the, finally, an example of the confidence ellipse. And what's interesting, just using the three amalgamations, a three-part composition made up of these three amalgamated parts, you get a perfect separation of the, and all pairwise, all these groups pairwise are significantly different. And I'm not showing p-values here, but I can put money down that all five of them are pairwise significantly different. Okay, here's my clustering. Two types of clustering. Again, this amalgamation clustering, which is something very new. I have a paper about this, which I thought about simple summations of the parts to do the clustering. Okay, and as you're doing my criterion is the variance explained again. So as I'm building up, I'm explaining less and less variance because I'm amalgamating parts. But then you know exactly what you're getting. When you see two coming together, you know all you're doing is you're summing them. Whereas in the conventional log ratio distance clustering at the bottom, you're clustering by geometric means, which becomes a little bit complicated to understand what's happening exactly. But you can do either one you like and see the difference and make a decision which one you like or which one you can interpret more easily. So I have the A-clust function in Easy CoDA. Again, this is the only place where you'll find this type of clustering. And then the usual Ward clustering, which is clustering by variance by squared distance. This is in Easy CoDA as well. although you could do it in other packages as well. There's a ward function in ward clustering in regular R packages. And but this is one thing that's interesting here. I'm not clustering the samples, I'm clustering the columns, the parts of the data matrix. So I have to transpose the data. If I'm doing this lower clustering that you see, I have to transpose it, and then I actually normalize the parts across the samples, as if the parts were the samples and the samples were the parts. So you do a normalization of the transpose matrix, and then you do the ward clustering. If you want to cluster the samples, you just do the ward clustering on the matrix in the untransposed form. Okay, I'm getting quite fast to the end. There's going to be one little bit of a major topic after this one. This is just to show you how I did the classification tree. If you're interested in doing something like that, you first of all have to get all the log ratios, the pairwise log ratios. For the kimberlite data, you have to get all 231 of them. So I have a function called LR. And if you do LR of the original data matrix, again, weight equals false, and you pay $LR, that means you're going to get this component contains the 231 log ratios in columns. And then you use that as your predictor matrix in the classification tree function, which is rpart, recursive partitioning in the rpart package. And that will compute this classification tree that you see here. Okay, there's one more topic, and I'm probably going to finish a little bit earlier, I hope. Yes, I think I'll finish earlier for a change, and give Eric a bit more time for the last part. And this is about correspondence analysis as a way to deal with zeros. I don't have time to explain exactly what correspondence analysis is, except to say that it is a widely used method in ecology, also where you also analyze compositional data, relative abundances, for example, and these are called profiles in correspondence analysis jargon. And correspondence analysis can handle data sets with lots of zeros. That's why it's so popular in ecology and in archaeology and in linguistics as well. It structures between sample and between part distances using a different distance function called the chi-squared distance. There are two main points that I want to make here. First, if the data are all positive, if your compositional data matrix is all positive, you mean there's no zeros in it, then the chi-square distance of the Box-Cox power transform data, now we heard about what Box-Cox was earlier by Eric. If you Box-Cox transform your data, then the chi-square distance actually converges to the log ratio distance as the power tends to 0. Now, that's an amazing thing. You know, I learned about correspondence analysis in the 70s, and I learned about log ratio analysis in the year 2000 when I met John Aitchison and also met Paul Levy. But then I never thought of them as being connected. They were like two different analyses completely. And then I discovered this and published the fact and showed that the chi-square distance converges to log ratios as the Box-Cox transform power, that lambda that Eric had, tends to 0. So in other words, correspondence analysis converges to log ratio analysis. But it's only when there's no zeros in the data. So you've seen this plot that I've got here. You'll see the blue line. You have to read it from the right-hand side. Now, I've got the kimberlite data actually didn't have any zeros in because somebody kindly had replaced the zeros for me beforehand. And if you go from the right to the left, you'll see that that blue line, the Procrustes, I'm plotting the Procrustes correlation, starts at about 0.731 for the untransformed data. And as that power transformation goes to the left to 0, you get to a Procrustes of 1. That's just to demonstrate to you empirically that it works, what I've just said. Okay, you can prove mathematically that it works. Now, what happens with no zeros? That works for no. What happens if you do have zeros in the data set? Well, what I did to test this out, I physically changed 20% of the data in the kimberlite data set, I changed them to 0, exactly to 0. I took the 20% smallest numbers, okay, the relative numbers, the compositional numbers, and then I made them 0. And that what happens now when you do the Box-Cox transform and you're doing correspondence analysis, remember, and you can see for a long time that dashed line, the dashed curve follows the no zeros one, but at a certain point it starts tumbling down, because as you're getting the powers going down, you remember we're getting closer to a log transformation, and so this thing is going to break down when you've got zeros. But you do reach a maximum point. And the maximum point in this particular case, just luckily, is right in the middle, which means that the 0.5 power, which is square root transformation, looks like a good one. And we are getting a Procrustes of 0.875. So that's how close we are to the, let's say, to the ideal. But of course, with zeros, there is no ideal. But we can at least take that as a measure of some optimality that we are getting. And you know, we haven't replaced any zeros, and that's the benefit of this. So if I now take the correspondence analysis and do the square root transformation, the Box-Cox transformation with square root, this is what I get. Okay, now I'm getting my parts again, but I'm getting slightly different parts that I had before. And you might notice that I'm getting parts that are have the higher abundances. They're not the rarer parts that we had before. And that's because correspondence analysis does weight the data. I've been mentioning this weighting a few times. It does weight the data, but at the square root and at the lower powers, the weighting is going to attenuate, be attenuated, and the weights are tending to be equal as the power goes down. But at least at the square root, there's still some higher weights given to the higher abundance elements here, and the lower weight to the lower abundance ones. I don't want to get too much into this weighting, so it's a separate topic at the moment for us here. Don't want to make things too complicated for you. Notice we're still getting a good separation of the groups, and we're getting more or less the same configuration as before. I can show you the once more these confidence ellipses, and you see they're nicely separated again. And using correspondence analysis, not log ratio analysis, but approximating the log ratio analysis and not having to replace the zeros. Okay, so that's my little story finished. I think I'm a little bit ahead of time, 5 minutes, I think. And I hand back to Ariadne and over back to Eric. Okay, thanks a lot. I'll see you later on.
Okay, so my final presentation here is process prediction and predictive mapping. This is using a lot of the multivariate methods that have been discussed by Michael and things that were described earlier, with some practical examples. So I described two important aspects of this. One is process discovery. I mentioned that earlier. We use the use of empirical methods for identifying structure in the data and forms the basis or justification to build or test models. So we start off by adjusting the data for censoring missing values in the form of imputation, and then we transform the data into log ratio space, whether using ILR, CLR, ILR, or any of the methods that Michael discussed in terms of log ratio analysis. And the use of different metrics, whether that's principal component analysis, LRA, or the T, distributed stochastic neighbor embedding, independent component analysis, UMAP, there's many different metrics you can use to observe and discover patterns in the data. From practical experience, I've found that it's useful to apply 2 or 3 of these different metrics because they show patterns that are quite unique and can describe processes that are otherwise not obvious. So the discovery of processes through empirical analysis is an important component of carrying this out. And from that, you can then determine suitable classes for predictive mapping, such as lithologic units, or they could be agricultural units, features of alteration, mineralization. And then you tag these classes to the sample sites where available using a geographic information system. Well, the process of predictive mapping, you start first with process validation, so the use of model methods for process confirmation, using techniques such as analysis of variance to determine which elements or principal components give maximum separation of the classes, and whether you get any separation at all. And then methods of classification used for prediction, whether that's linear discriminant analysis, quadratic discriminant analysis, neural networks, logistic regression, random forests, XBoost. There's many different classification methods that you can use. And the classification to determine the measures of posterior probability or typicality from which a probability of class membership can be assigned to each site or each sample. Other methods can be used, in this case, I typically like to use random forests. And then carry out spatial analysis to carry out semivariograms and subsequent kriging to produce predictive maps for each class. And then from this process, you calculate the accuracy prediction and overall accuracy. You can calculate measures of precision, fraction of true positives over true plus false positives, or measure of recall, the fraction of true positives over false negatives. And the estimates of accuracy are derived from process validation and based on the confusion matrix of predicted classes versus actual classes. So we'll go back to the Kimberlite story. And I showed this slide earlier. And these are the messy looking hand samples that show just how difficult it is to classify these various phases optically. So on the left is the scatter plot that I showed earlier, and in the middle is a principal component biplot based on the CLR transform that Bruce and I worked on quite some time ago, and where we isolated the 5 different phases. And what was important about identifying these phases was that we were trying to determine which phase had higher grade diamonds versus those that would have lower grade diamonds. And you can see here in the green, the areas enriched in silica, nickel, chrome, cobalt, magnesium, represents mantle contamination brought up by the kimberlite magma. And the areas where you see crust contamination, which is shown by principally the presence of feldspars, you get a relative enrichment in aluminum, sodium, potassium, and rubidium. And then you see the kimberlite fractionation pattern, which represents things like calcium, phosphorus, niobium, lanthanum, thorium, etc. And these are the same patterns that Michael showed in his previous log ratio plots. And what was also, if you look at the scree plot, you can see that, go back, that we have basically 3 principal components that account, 4 principal components that account for most of the variability of the data, and then the remaining principal components sort of represent either undersampled processes or random processes. So the first four principal components account for 80% of the overall variation. So we carried out a linear discriminant analysis to validate these different phases. And on the left, you see a plot of the first linear discriminant versus the second linear discriminant. And we can see again with the ellipsoid hulls around the phases that we get a significant overlap between the early jolly food, the pence, and the cantuar. And we see this fairly distinct change in phases from early to mid to late jolly food. We have the accuracy matrix on the right, and you can see that we're getting better than 90% classification accuracy, with the exception of the late jolly food. And the overall classification success is greater than 95%. Okay, now moving on to much larger data sets, looking at the TELUS data from Northern Ireland. This was an area in Northern Ireland sampled. There were 6,862 sites. The surface soil at the A sampled at 5 to 20 centimeters depth. We carried out XRF analysis and ICP analysis. And there was also a deep soil, what we call S sample, sampled at 35 to 50 centimeters depth. So we're looking at a very dense survey here, one site to every 2.4 square kilometers. We looked at the age brackets of the area. So on the left is the legend for the age brackets. And so these are generally lithologically distinct, but there's going to be a lot of overlap in several of these classes because you have things like limestone, mudstone, sandstones, all in the same age bracket. And so the degree of distinction will always be somewhat problematic. This is the sampling of the region, the sample sites, and coded by the age bracket, as you see on the left. Now, we carry out a principal component analysis on the XRF data, and on the left is the scree plot, and we can see that there's about 4 or 5 principal components that really define, let's call them the geochemical or physical processes, and the remaining eigenvalues just represent undersampled or random processes. And on the right is a principal component biplot, and we see, again, coded here by the age bracket, and the red triangles represent the basalts in the northern part of Northern Ireland. And then we get a mixture of Phanerozoic sequences that were shown here along the negative PC2 axis. And then we get an area where there's a lot of peat, and that shows a mixture of both the Phanerozoic sediments and the volcanics of the Cretaceous here. So we're seeing 3 principal trends in the data: the basalt, the granites and sandstones, and then we get the peat, which is fairly prevalent throughout much of Northern Ireland. So looking at this data, we're considered looking at an amalgamation, sort of a fit for purpose approach here. Well, there are cases where the groups of elements are highly associated or correlated, such as rare earth elements, where elements combine in specific laticites in minerals. These elements can create difficulty in linear algebraic methods where collinearity can result in non-unique solutions. This is also a problem, as Michael discussed earlier, about when we're using centered log ratios and we're using the geometric mean. Because the geometric mean is multiplicative, you can get you get results that are difficult to interpret. So grouping these elements and amalgamating them reduces the risk of collinearity and simplifies the identification of processes. So we amalgamated the elements this way: light rare earth elements, heavy rare earth elements, mafic elements, and then the elements representing feldspars, barium, sodium, potassium, and then feldspars, anions, aluminum, and gallium. So if we look at the non-amalgamated scree plot, we see here about 4 or 5 dominant principal components. And when we look at it amalgamated, we see a slightly different interpretation, not by much, but enough that it is actually a bit different. And we look at the biplots for these, and you can see here on the left was what I showed earlier, the basalts and the sediments, the Phanerozoic sediments, and then the areas that have the peat enrichment here. And you can see with the peat enrichment, you have a lot of chalcophile enrichment, and where you get chalcophile elements absorbing onto the carbon-rich material. Now this on the right is the amalgamated solution. And here we've got the mafic elements here, the rare earth elements here, and the unfortunately I have something blocking this there. We can see here the chalcophile elements here. So this right biplot is actually flipped, and so this is actually represents the peat enrichment here. But essentially the patterns are the same. So using the amalgamations actually simplifies things. Now we can also look at analysis of variance to see how distinct these various age brackets are. And if we just use the elements, we can see that we have more than 20 to define a useful discrimination between these classes. But if we use principal components, we only need about 8 principal components to show the difference between the classes. So working with the principal components seems like a more sensible way to separate the classes for any kind of prediction. So this is the result of a discriminant analysis. On the left is the first versus second discriminant analysis as the material was logged or tagged in the geographic information system. And on the right is the predicted classes from the linear discriminant analysis. And we can see they're almost identical. We see here that there are some areas here where they have been reclassified as basalts and not the, I believe these are the Mesozoic or not sure exactly what this age bracket represents now, but they are, you can see here, there's quite a bit of dispersion with this class here and less dispersion here. Then we look at the classification accuracy. We have an error rate of 30%, or let's say a classification success rate of roughly 70%. And we can see which classes are not well classified, and some are quite well classified. And so some as low as 7% or 6%, but some as high as 85%. So it's highly variable, and that has to do with overlap or compositional overlap of these classes. As I mentioned earlier, several of the age brackets have very similar compositions, so we would expect overlap in this. So a measure of distance, of Mahalanobis distance, is measured given from a given observation, the sample site, to the centroid of each age bracket class. And the distances are based on the principal components used for the classification. And the predicted class is assigned based on that shortest Mahalanobis distance, which is a posterior probability. But the posterior probability is a forced fit. So an observation must belong to one class. And that it could be that you have a sample site that actually doesn't belong to any of the classes, but by definition, using a posterior probability, it'll the shortest distance, whatever that distance is, that will be the class that it is assigned to. So here are measures of posterior probability for the different age brackets. So on the left there, the felsic, that I've got that labeled incorrectly. This should be the Cenozoic basalts here, and these are the felsic granitoids here. So those labels are flipped, but you can see that they are quite well predicted. High posterior probabilities for both here, 0.9 to 0.1. And if we look at sand and lignite here, you see from the Cenozoic Paleogene Oligocene here, it's not a very good classification at all, just a few sites here, and they are quite low. Same for the Mesozoic mudstones. They're in this region here, and they're not well predicted. And there's a lot of overlap with other classes. We look at basalts, trachytes, cyanites in these western part of the region here. We see fairly good classification, but we can also see that it's also distributed throughout this region here, representing some overlap or confusion. And then the apenite suite, which is granites and granodiorite in this region here, are very well predicted. And then we have basalts and andesites here in this area region here. They are fairly not well predicted at all, and there's a lot of overlap with their surrounding classes. And then for Paleozoic clastic rocks in this region here, we get a fairly good prediction in much of the area, but some overlap region here and also in this region here. And then the Paleozoic gabbroic rocks in this region here is not well predicted, and mostly because it's overwhelmed most likely by the surrounding soils. And then this is the Neoproterozoic rocks, which are samites and metamorphic sediments, is well predicted in some areas and less well predicted in others. So moving on now to, so that's looking at the soils in Northern Ireland, and we're going to look at next at the TELUS data, and it's not from Northern Ireland, it's from the Republic. That's a mistake I made this morning, so pardon me. So this is the evaluation of TELUS waters geochemistry in Northwest Ireland. And the Geological Survey of Ireland carried out a geochemical survey of surface waters in which there were 6,739 stream water sites that were sampled and studied. And the intent was to examine the usefulness of surface waters to reflect natural and anthropogenic influences. So this is a map of the sites, the sampling sites, and the various underlying lithologies in the region. And this southern region here is mostly Cretaceous or various forms of carbonate rocks. And on the northern part are metamorphic rocks of Neoproterozoic age. We're looking at a principal component analysis of these data. We see again about 5 or 6 principal components that would be considered significant, the rest being undersampled or random. And we look at a principal component biplot here. We can see that calcium, uranium, strontium, fluorine, molybdenum are associated here with the limestones. But this also reflects the agricultural effects of fertilizer going on the region where there's limestone, because that kind of terrain is used a lot for agriculture. So we're seeing some anthropogenic effects in the data. And here we see various forms of silicate and clastic rocks along the positive. Whoever's talking, can you turn off your microphone, please?
Ho fatto vedere, cioè sapevo di questo studio, avevano fatto le formiche, però poi non avevo visto niente. Ma fanno
Excuse me, Federica, your microphone is on.
C'è paura se ti trovi in basso.
Turn it off.
Okay. All right. So if we look at the random forest prediction of rock type, we can see here with the significance and using this mean decreasing Gini value, you can see that principal components 1, 5, 2, 7, and 9 provide the best class discrimination between for the lithologies in the waters data. And here's the counts of the prediction and how well they're predicted, and and here are these accuracy in percentage. You can see that for some rock types, there's very high prediction, and others there's zero, meaning that they're just not predicted well, and that's mostly due to the overwhelming effect of many samples belonging to one class and the statistics involved in the random forest calculation to estimate these. So that is a problem with some of these classification methods, is the representation or underrepresentation of some classes in the sample population. The overall accuracy is 70%, which is considered reasonably good, but still problematic because we have these zeros here. And we can look at this in terms of how each of the lithologies are predicted. And for example, here we look at PC1 versus PC2, and we look at the posterior probability of the prediction. For, let's say, amphibolites, we can see that what part of PC1 versus PC2 has elevated posterior probabilities. In the case here of limestone, we see here that negative PC1, negative PC2 has higher limestone. And if you recall back to the principal component biplot, it was the negative quadrant, PC1, PC2 quadrant, that is relatively enriched in limestones. So we're seeing that reflection in the prediction. So this is the same thing with PC5 versus PC7, and we can see some better classifications or increased posterior probabilities for some of the classes, but also we see is essentially zero for other classes. So this is a problem. So we look at the interpolated images of these posterior probabilities of the sample's water sites on the map. For limestone, we can see that the higher areas of limestone prediction are in the areas to the south central part, which is where all the limestone occurs. We look at gray wackies, we can see there are some in the region here in the west and here in the eastern part of the sample region, which fits with what we know about the lithologies. And for amphibolite, we see moderate classification here in the northwest and a few sites of amphibolite in the western part of the region. And for granites, we can see here, this is a map where we've just reduced the influence of the low posterior probabilities. And also I've just put the, for each sample site, I've put or graded the sample site according to the posterior probability. And here, the maximum we're getting for granites is 0.5, so it's not a high classification by any means, but it does highlight where the granites actually are. So looking at now, looking at surface sediment geochemical surveys for the prediction of major crustal blocks. This was done across Australia, part of the National Geochemical Survey of Australia. with Patrice de Caratat, Geoscience Australia. So there was a geochemical compositions of major, minor, and trace elements were determined on samples collected as part of the National Geochemical Survey of Australia between 2006 and 2011, which was run by Geoscience Australia, but the states and Northern Territory cooperated in the collection. The NGSA collected catchment outlets, sort of similar to floodplain and overbank sediment samples from two depths, 0 to 10 and 60 to 80 centimeters, in the sediment profile at 1,186 sites across Australia. The collected samples were sieved to 2 grain size fractions, less than 2 millimeter and less than 75 micrometers, and then analyzed geochemically, resulting in 4 separate data sets. And whole rock compositional data for 50 elements were used. So Australia is composed of crustal blocks representing, reflecting architecture of the continent. And the NGSA of Australia analyzed the surface regolith over the continent. The objective of the study was to use surface regolith compositional data for spatial prediction of membership to the major crustal blocks across the continent. Previous work had shown that the geochemistry of superficial materials, such as lake sediments and glacial tills that we did in Canada, can be used to define type compositions for the lithologies with which they represent based on statistical classification methods. So it's a map of Australia. I've highlighted here Laterite Geochemical Survey, but just to show the sort of the geology and the fact that a good 90% of Australia is covered by the yellow sedimentary rocks, which is basically recent weathering and wind-blown material. So we don't have a lot of bedrock on which we could do prediction necessarily. So a map of major crustal blocks of Australia was created, classically interpreted from deep seismic reflection data and potential field geophysics. And the fundamental geological units basically form the continent, and the boundaries are often crustal or lithospheric scale. Discontinuities, they may act as melt and fluid conduits in a mineral system, so they have sort of mineral potential significance. So in the colors of the different blocks, the confidence is shown here in terms of green having high confidence of the boundary, the yellow shows moderate confidence, and the red dashed lines represent low confidence. So in other words, there is some degree of uncertainty in terms of how good the separation is between these crustal blocks, and we will see the influence of that shortly. So we treated the geochemical data as compositional and applied logratio transforms, and we used the minimum maximum autocorrelation factors that was originally described by Switzer and Green in 1984, and applied an analysis of variance to these minimum maximum autocorrelation factors based on the major crustal block classification, and applied linear discriminant analysis to validate and provide a classification framework of these crustal blocks using non-robust estimates of covariance. Soft indicator kriging was used to interpolate the posterior probabilities derived from the linear discriminant analysis, from which we derived most likely crustal blocks and measures of uncertainty. So this is the result of that analysis, and we're looking at the classification accuracy. So on the table on the left, we have the 4 different fractions, the bottom of the outlet sediment, coarse grain, the bottom of the outlet sediment, fine grain, the top coarse grain, and the top fine grain. And then we have 24 crustal, actually 23 crustal blocks. The 17 is missing because we had no samples in it. And we can see here which crustal blocks were best predicted. For example, 14 was well predicted, 4 was well predicted, and 4 represents the yield iron block here on the upper left map. And we can see that it is fairly well predicted using the top outlet sediment and a coarse grain size fraction. The bottom size fraction, fine grain, basically shows a similar feature. That's for MZB4. For MCB02, we get not as high a prediction accuracy with more overlap in the adjacent crustal blocks. And we see that the top of the sediment coarse grain is marginally better than the bottom of the sediment fine grain. So we get a sense of how well we can predict these major crustal blocks from the sediments of the collected over continental Australia. So we can also estimate measures of uncertainty, and from the estimated posterior probabilities, the following measures of spatial uncertainty about the allocation of a location to a specific crustal block were computed. There was local classification of uncertainty, where phi is equal to 1 minus the maximum of the posterior probability. And we have local entropy given by h, where it is the sum of the posterior probabilities times the natural log of that posterior probability, where k represents the number of classes. So the local classification of uncertainty attains values from 0 to 1 and is close to 0 when class membership is reasonably certain. Similarly, the local entropy provides a measure of local randomness, and the maximum value is given by the natural log of k, which is attained when all crustal blocks are equiprobable, and its minimum value is 0 when the crustal block estimate is certain. So we produce these measures of uncertainty, and we can see here where we have low values. These represent areas where we have high confidence that we've estimated the crustal block fairly well. In this case, this is the top outlet sediment coarse grain, top outlet sediment fine grain, and this is the bottom coarse grain and the bottom fine grain. And we see there are differences between them, but they all outline essentially the same region. And we can also show measures of uncertainty, the measures of entropy. And again, we have lower entropy in areas like the Yilgarn in the north, and then the area here in the central east. And it's not as good for the bottom, the fine grain sediments, but better for the coarse grain sediments. So that pretty much finishes what I wanted to show in terms of how we can use multi-element geochemistry for predictive mapping and understanding processes in geochemistry. So I'll summarize here. Geochemical survey data are well suited for identifying processes associated with mineralogy, weathering, and transport. The use of multi-element geochemistry enables the recognition of processes through combinations of elements that reflect mineral stoichiometry. Soils, stream sediments, lithogeochemistry, laterite, etc., all have distinct mineral associations and are reflected in the inter-element associations. The Geospatial Association of Geochemical Survey Sites, with measures of underlying geology and superficial processes, record the influence of igneous sedimentary mineralizing processes and subsequent interaction with the biosphere, ecosystems, and climate. The use of advanced analytics and machine learning methods enhance the ability to discover and validate or predict processes. And the results demonstrated from predictive mapping confirm the capacity of geochemical data to test new hypotheses from which new geological geochemical process maps can be created. And the establishment of training sets, whether they be specific lithologies, alterations, soils, ecosystems, etc., can assist in the study and prediction in areas where there is a lack of information. So overlap between classes, such as lithologies, is expected, and the use of posterior probabilities can identify the degree of distinctiveness and overlap. So the use of advanced analytics and machine learning methods provide an objective, repeatable, and defensible framework from which processes can be identified, predicted, and validated. And I think that's the essential part of the message that I want to convey. So I have here a list of references that you could refer to in terms of what things were presented here today, and some other additional work. And I'll thank you for your attention, and we can, I guess, we have time for questions. In the ILR school, there's the transformation called pivot coordinates, where you can actually calculate the correlations between these pivoted coordinate variables. It's used by some people as a means for looking at pairs and getting a correlation coefficient. I tend not to go that way because I like looking at everything in the multivariate context, and in fact that's what I advocate, is a multivariate approach thing. So I wouldn't use something like pivot coordinates, but I know others have, and it could be useful depending on the application.
Thank you. Thank you, sir.
Actually, I notice here that Bob Garrett is present, and Bob has actually published something on the use of pivot coordinates. I don't know, Bob, would you be interested in commenting on that?
Yes, thank you. Well, it's not really my work. It was work. It was carried out by King Clover, Peter Filsmoser. I think Ron was involved, and I was very much a bit player at the end. And I was interested in it. And there is a very short article in the Association of Applied Geochemists journal called Episodes, where I showed how, taking a very simple set of igneous petrology, you could generate correlation coefficients that made sense. That's all I have to say. I found it interesting.
Yeah, thank you. Thank you very much.
Thanks, Bob.
If you are okay with the questions, I think it's time for the nice surprise. Michael?
Is Alekos going to close off before, or must I just go into the surprise?
Because I see that people are leaving little by little, but I think it is something not to be missed.
Okay, well, here it is then. It's a statistical sum about compositional data analysis. And I had to have a little bit of single malt before this just to get the voice right.
Cheers.
Ah, that's good. It's CoDA time. Compositional data analysis is easy. Models are fitting. Explained variance is high. Your data are rich. Log ratios good looking. So hush, geochemists, don't you cry. So hush, geochemists, don't you cry.